All right, let's talk about a fundamental rule that pretty much runs the world around us. I mean, from the air we're breathing right now to the coffee that wakes us up in the morning, we're diving into solutions. And we're going to figure out why some things mix together like they're best friends, while others, well, they just won't. So yeah, let's get into it. You've definitely thought about this before, right? You stir a spoonful of sugar into your tea and poof, it's gone, vanished. But then you try to do the same thing with a handful of sand and a bucket of water and it just sinks. It sits there at the bottom staring back at you. What is going on there? It's not magic, it's chemistry. And by the end of this, you'll know exactly what the secret is. So, first thing you need to realize is that you're already kind of an expert on solutions. Why? Because you're interacting with them all day, every day. They are, and I mean this quite literally, all around us. And what's so cool about this is the variety. I mean, think about it. The air we're breathing, that's a solution, a mix of nitrogen, oxygen, and a bunch of other gases. The soda you're drinking is a solution of carbon dioxide gas and sugar solids dissolved in a liquid. And get this, even solid things can be solutions, like the brass in a trumpet, which is actually solid zinc dissolved in solid copper. Wild, right? Okay, so what officially makes something a solution? Well, it's a mixture that's so perfectly blended together, so uniform, that you can't see the individual bits and pieces anymore. And in every solution, you've got two main players. There's the solute, that's the thing being dissolved, like the sugar. And then there's the solvent. That's the thing doing the dissolving, like the tea. You can think of the solvent as the party, and the solute is the guest that's mixing in with the crowd. So, how does a solvent decide which solutes it's going to let into the party? Well, chemists have this really simple, super elegant rule of thumb that explains pretty much everything. It's like the secret password to get into the solutions club. And that's it. Just three little words: like dissolves like. This is the golden rule, the core principle of it all. It means that substances that are chemically similar to each other will mix together and form solutions. So the big question is, what exactly does it mean for two molecules to be like each other? Before we get to that, let's put a name on the actual process. When a solute dissolves, its individual particles are literally ripped apart and completely surrounded by the solvent particles. The technical name for this is solvation. And because water is such an incredible common solvent, we give its specific action a special name: hydration. And this picture shows it perfectly. On the left, you've got regular old table salt, sodium chloride, all neat and tidy in its crystal structure. But the second you drop it in water, the water molecules just swarm it. You can see on the right how they pull the sodium and chloride ions apart, totally surrounding them. That right there is hydration in action. It's a total takeover. Okay, so we've seen what happens during dissolving, but to really get the why, why water can just dismantle a salt crystal like that, we need to dig into what makes molecules like one another in the first place. This is the real question, isn't it? We keep saying like dissolves like, but what is this likeness? Is it their size, their shape? Nope, it's something way more fundamental, something you can't even see. It all boils down to a concept called polarity. And polarity is all about how atoms inside a molecule decide to share their electrons. You can see on this chart that if atoms share electrons pretty evenly, they have what's called a non-polar bond. But if one atom is way better at grabbing electrons than the other, you get a polar bond. And if one atom just steals the electron entirely, well, that's an ionic bond, like in our salt. So let's just cut to the chase. It's all about electrical charge. Polar molecules, like water, are basically tiny little magnets. They have a slightly positive end and a slightly negative end. Nonpolar molecules, like oils and fats, have their charge spread out all nice and even. So, like dissolves like just means that polar magnets want to hang out with other polar magnets, and the neutral nonpolar molecules prefer to stick with other nonpolar molecules. Simple as that. Okay, so we've got our main rule down. Polar dissolves polar, nonpolar dissolves nonpolar. Makes sense. But what happens when we throw a wrench in the works? Like temperature. I mean, if you want to dissolve more sugar in your tea, you use hot tea, right? Well, it turns out that when it comes to heat, the rules get a little weird, a little unpredictable. Just look at this data for a second. We've got two really similar salts, and we're dissolving them in water as we crank the heat from room temp up to boiling. Now, look at the top one, sodium chloride, our table salt. Its solubility barely changes. Not impressed. But then look at potassium chloride right below it. Whoa! Its solubility jumps by more than 50%. Same solvent, super similar solutes, but they react to heat in completely different ways. And yeah, this unpredictability is true for tons of things. For most solids, turning up the heat helps you dissolve more, no problem. But for some other solids, and for all gases, heat actually makes them less soluble. That's exactly why a warm soda goes flat so fast. The gas just can't stay dissolved in there. And then you have the weirdos like table salt that just don't seem to care what the temperature is.
So, how in the world do scientists keep track of all this chaos? They can't just memorize every single substance's quirky relationship with heat. No way. Instead, they use this incredibly powerful visual tool to map it all out. They use something called solubility curves.
And here we go. Now, this graph might look like a messy plate of spaghetti at first, but it's not. It's actually a storybook. Each one of those colored lines tells the unique story of a specific substance, and it shows you exactly how much of it you can dissolve in water at any temperature you can imagine. And reading it is actually super easy. All you do is pick a temperature you're curious about on the bottom, go straight up until you hit the line for the chemical you care about, and then just look straight over to the left. That number on the side, that's your answer. It's the maximum amount you can dissolve. The really fascinating part is when you start comparing the different personalities of these lines. I mean, look at the blue line for KNO3. It practically shoots straight up. It loves the heat. Then find that light brown line for NaCl, table salt. It's almost perfectly flat, just like the numbers we saw earlier. And then look at the light blue line for NH3. That's ammonia gas. It's going downhill. The hotter it gets, the less of it can stay dissolved. Every single point on every one of those lines represents what we call a saturated solution. Think of it as the full point. The solvent is holding the absolute maximum amount of solute it can possibly handle at that specific temperature. If you try to add just one more tiny crystal, it's just going to fall right to the bottom. No more room at the end. So we figured out the rules of polarity, we've seen the crazy, unpredictable effects of temperature, and we know those lines on the graph are the absolute limit. But what if I told you there's a way to break that limit? A way to actually cheat the system and trick a solvent into holding way more than it's supposed to? Think about that for a second. How could you possibly pull that off? Well, that's a story for another time.